Let's barge in the first topic of this week. We're going to be talking about difference equations. So for ODEs, ordinary differential equations, or PDEs, when we're talking about differential equations, there are two letters missing here. We are talking about a time that belongs to the real numbers. So the time continuously changes. For difference equations instead, we expect time to be integer, or sometimes even restricting to positive integers. So the time is discrete, the time is jumping. What is the difference between the two? Well, ODEs are something that represents a continuous, smooth change. So for example, if you're looking at a glacier flowing, even if it's slow, you are expecting the glacier to not just jump, but just smoothly change over time. So you have to keep track of what is going on. Well, sometimes you have information either on discrete times because you're only able to see it at discrete times, or because it is intrinsically a discrete time process. For example, you're counting the number of rabbits per generation. So that is a discrete problem. The time doesn't flow in any sense. What you're counting is different generations, and you're checking the number of rabbits at generation 1, generation 2, and so forth. This is the difference between difference equations and differential equations. And for differential equations, we were dealing with a derivative. So the unknown was y, and we have information about how y prime behaved. Instead, in the difference equations, we are going to approximate derivatives, similar to what we did in the Euler's method. So instead of having y prime, we have yn plus 1 and yn. So y computed at time n plus 1 and y computed at time n, maybe with a rescaling. And those are the information we have about. When we look at first-order difference equations, we usually want to formulate it in this format. We have yn plus 1 equals f computed at n and yn, with n a natural number, including 0. It's first order because the difference between the left-hand side and the lowest value of y, of the index of y that is appearing, is 1. So here we have n plus 1 on one side, n on the other, and the difference is 1. So for example, if we had yn plus 1 equals something depending on yn minus 1, then n minus 2, then the difference between the highest index and the lowest index is 5, so it's a fifth order difference equation. We also want to look at first order difference equations. And a first order difference equation is linear if f is linear in yn. So for example, yn plus 1 equals 3yn squared plus other things. It's not linear because we have a term that is yn squared. On the other hand, if we have yn plus 1 equals n to the third plus nyn plus yn, it is linear because every single term in here only has yn appearing at the first power at most. So this second example is linear. As is the case for ODEs, also in difference equations we need to know where to start. So we have an initial condition that is usually y0 equals to some value alpha. If f doesn't depend on n, so equivalently to the autonomous systems, and we find a value xi, such that xi is equal to f of xi, then if you put yn equal to xi, then yn plus 1 is going to be equal to xi, yn plus 2 is going to be equal to xi. Every single thing after that is going to be equal to xi. So if you start xi with y0 equal to xi, you're going to stay there forever. It's an equilibrium solution. It's the equivalent of the continuous equilibrium solution. Let's use difference equations to model population dynamics. Let's go for it. The idea is that in this case, we're checking on the population every so often. A month, a year, a generation. Either way, we're not keeping track of every single second in which the population is changing. We're only looking at it with a distance, with a time discontinuity at each step. So the first model is a linear dependency. The population at the next year depends on the population this year plus a coefficient. And the coefficient might depend on the year itself. So the first year, the population is going to be rho 0 times y 0. Then the population is going to go to rho 1 times rho 2 times y 0. And every single iteration, you're going to just get a coefficient in front of your population at time 0. If we assume that rho is constant for all n's, then we can write yn plus 1 equals rho times yn. And by going through the same steps we just did, yn is equal to rho at the power n multiplied by y0, that is our initial condition. If we take the limit of this, what happens? Well, we're trying to figure out if we just leave the population be and come back in infinitely long time, what happened to the population? If rho is smaller than 1 in absolute value, then every time we multiply by rho, we are decreasing the amount of the population, so the population tends to 0. The limit for yn for n tending to infinity is equal to 0 for rho between minus 1 and 1. If rho is exactly equal to 1, then the population is not changing. While for every other value of rho, the limit does not exist. Is infinity if rho is positive, and if rho is negative, it keeps switching. So looking at this, we notice that, well, for rho equal to 1, we stay there, but for rho slightly less than 1, all the solutions tend to 0. So y equal to 0 is an equilibrium solution, first of all, and is asymptotically stable for all values of rho smaller than 1. So it doesn't matter anymore where we start. For any y0, as long as rho is in absolute value smaller than 1, y equal to 0 is asymptotically stable. Everything tends to it. You can imagine that as saying that the population is decreasing every single year. That is what rho smaller than 1 is telling you. So at some point, you're going to have no population left. Let's go for a more complex model. It's still a linear model, but in this case, we have, on top of the linear coefficient, also a term that is immigration. If it's negative, it's emigration, but we don't really care about that. So we have that yn plus 1 is equal to rho, that is our coefficient of population growth or decrease, multiplied by yn, plus a coefficient bn. Again, for n going from 0, 1, 2, onwards. Then we have y1 is equal to rho y0 plus b0. y2 is rho times y1 plus b1. So rho times rho y0 plus b0 plus b1. So it's rho squared y0, sorry, there's a square missing, plus rho b0 plus b1. And y3 is rho to the third y0, rho to the second b0, rho b1 plus b2. If you keep doing this trick, you can compact the notation by writing that yn is equal to rho at the end times y0, that is the growth of your population independently of the immigration, plus a term that depends on the immigration. That is bj, the population at time j, multiplied by rho times n minus 1 minus j. And we're summing from j going from 0 to n minus 1. It's a special case if the immigration is constant. So for bn is equal to b for all n. Then we can write it in an even nicer way. Yn is equal to rho n y0 plus 1 plus rho squared plus rho to the third up to rho at the n minus 1, all of that multiplied by b. If rho is different than 1, this multiplication of b can be rewritten as 1 minus rho to the power n divided 1 minus rho. And here you notice nicely how the first part, rho n times y0, is the original population growth, or decrease, and the other section is immigration effects. We can rewrite things a bit better, and we have yn is equal to rho to the n of y0 minus b over 1 minus rho plus b over 1 minus rho. And if we look at this, we want to study this behavior a bit better. We want to see if it asymptotically tends to something or other. And what we see is that for rho equal to 1, well, we have fractions with 1 minus rho at the bottom, so this equation is not valid. Also, at the previous slides, we said that rho needs to be different than 1 in order to apply our approximation. So for rho equal to 1, this equation is not valid, and we cannot compute that here. If rho is smaller than 1, then the first part that is multiplied by rho at the power n is going to tend to 0. So yn is going to tend to b over 1 minus rho. Otherwise, if rho is either equal to minus 1 or it's an absolute value bigger than 1, if we have that y0 is equal to b over 1 minus rho, then the first term disappears, and yn is equal to b over 1 minus rho for every n except 0. Otherwise, there's just no limit. It doesn't work. What happens for rho exactly equal to 1? Well, here we need to backtrace a little bit. We have to get back to our equation, and for rho equal to 1, our equation becomes yn plus 1 equals yn plus b. Then we have y1 equals y0 plus b, y2 is equal y1 plus 2b, and so forth. So it is not bounded. If b is positive, it tends to plus infinity. If b is negative, it tends to minus infinity.